So, Bismillah ar-Rahman ar-Rahim. Now we are going to start our 8th lecture in M269, and it's going to be about search, just to continue what we have started in our previous class. Here we are going to talk about the naive string search algorithms that are very simple in terms of searching for string patterns in a given text, and then we will move to more advanced and more efficient algorithm that is called the KMB, and we will come to the abbreviation later, and that is actually very popular in searching for patterns in large DNA databases. So this it has actually different applications. And the last one will be on the binary tree, and especially we talk about the AVL tree, and to show how we can use it to enhance the complexity of the searching algorithm. So the KMB will be actually, it stands for the Nath-Morris-Pratt algorithm. That is stands for the name of the founder of this algorithm. So the KMB stands for the first or the initial letters of their names. And actually for the AVL, we will talk about the trees, different trees, the binary trees, but the AVL tree will be a self-study. So you need to study it by yourself. Please access the GCC page on LMS to access the study guide available on that page. So I hope you pay attention today for this topic, as especially for the KMB, where actually some tricks are there compared to the rest of the algorithms. So now what we need is to searching for keywords or a text, a huge text. So let's say, for example, when you use your Google, you are actually using a search engine, and the core of that search engine is based or built based on a given searching algorithm. So the better is the searching algorithm, the faster is the result. So that's why everybody likes Google. It's because of how fast is Google in applying the search and getting back the result for the users. And actually that is based on, that's the reason behind such performance is the right choice of the search algorithm that the search engine Google is using. So what do you mean by search? Search means we are looking for a pattern B that is existed in the text T. So that is the whole text, and we are looking for a keyword or part of the text in T. So we call it P as a pattern, and we call it the T as a text, the whole text. So GCT, the pattern GCD is already existed here in blue. So the P is part of T. So many times, even if you are using the Word document, the word processor from Microsoft, and you are looking for a keyword, you just press the control with F, and then you write whatever text you are looking for, and then the search function that you are using in Microsoft Office Word will guide you to the location of that word. So what we want here is actually to find where do we have, or whether we have a match between the pattern in the text or not. And before that, let's go through some important terminologies in the field. So given a text in this way, so the length is denoted by the two sticks. It's like the determinant, right, in math. So this one to indicate the length. How many letters do we have in the text? And we have the substring, like what you can see here. GCT here, the GCT is substring of S, means GCT is part of S. That's what mean by substring. We can also say CTT. CTT is a substring. طب can we say A is substring of AGCTTGA? Can we say that? Definitely yes. Because A is a string of length 1. So A is a substring of S. Subsequence. Subsequence is if you take out some of the letters from the original S, from the original text, does it keep that? Does the text that you have meet the same positions as the original S or not? For example, see the original text A, G, C, T. Can we say that A, C, T is a subsequent or subsequence of S? Yes. After you delete the G, you still have A, C, C, T, T in the same position. So we can say that ACT is the subsequence of S. Prefix is actually the first string or substring of S, which include at least one letter or one position. So AGCT is actually the prefix of this text. Why? Because it is the first 4 characters. Someone may say, no, I don't want the prefix to be like this. I want the prefix to be AGC. Correct. Someone might say, I want to consider A as a prefix. Also correct. It is the first letter. But we cannot say GC is the prefix. It must include the first letter as minimum. And the opposite for the suffix, where we can consider A as a suffix, we can consider GA as a suffix, we can consider TGA as a suffix, we can also consider TTGA as a suffix. Any questions up to this point? Okay. Now, the simple algorithms that are used for searching is called the brute force algorithm. In brute force algorithm, you need to try every single possible solution. Not allowed to skip any single solution. And this is actually one of the attacks that are used in security. For example, I will tell you that your password is for your ATM machine, your password is composed of 4 digits, right? 4 digits. What type of attacks we can apply on ATM machines? We can say, okay, let us try the brute force attack. It's called brute force attack. So the term brute force means trying every single possibility. So what they do to attack your ATM account, your ATM card, is to try every single combination of letters. So they will start with 0001, 0002, 0003, and if it doesn't work, then 0010, 0011, 0012, and so on, until they reach 9999. Because your passkey, the password, the digits, must be combined, a combination of 4 digits between 0 and 9. Each digit has a range from 0 to 9. So you have 4 different digits, and each digit has has 9 possibilities. So I know that it's a huge amount of possibilities, but if the banks did not block your card after 3 trials, then anyone can attack your card. because what they do actually, they don't do it by hand. They program some chips, electrical chips, which can perform such computation in a very fast way. So that's why your bank will block your account after 3 trials or 4 trials. And the same thing happened to your password, by the way, your email password. If you fail to enter your password multiple times, it will block you. This is for security reasons, to prevent such brute force attacks in your account. So how this work in searching algorithm? Let's say you have this text which include these letters, and then you are looking for the patterns A, G, C, G, G in here. What you do is to compare the first A with the first A, the first letter A, first position with the first position. If works, correct. Then compare G with G. It works, yes. C with C, yes. G with C, no. So what we have to do is to shift the pattern B one position to the right. Again, A, starting from position 2. So we compare A with G. It marks no, no match. One shift to the right. A with C, no match. One shift to the right. A with C, no match, and so on. So you need to trace, or you need to track every single position of P that match the positions of T. You stop when you found it, if you found a pattern. Otherwise, you will reach to the point where this one is compared to the last item here. Yes. Okay, so this is very simple type of algorithms, but it's not efficient at all, and the complexity is very high. It's OMN, MN type. From where we get the M and the N. Actually here, for the text, you see here, for the text you have P. The text has M characters, and the B, I mean the pattern, has M character, and the T has different characters, of course not of the same size. That's why we say here we have N character and here we have M character. So you need to compare every single M with N. Every single M with N. You see, we're shifting every time A and compare it again with N. So the time taken is M by N. That's why we say the complexity is OMN. Clear? Okay, good. Now, this is how the brute force attack actually works. This is the code. You can go through the function. It's very straightforward, only shifting the J. This is for the button by 1 if there is no match. Of course, the worst case, the MN is for the worst case. Yani the best case, you might find your button from the first trial, from the first round. But the worst case is when you have this kind of cases. If the text is A then H and the button is AH, you see what will happen? You have to compare AA yes, AA yes, AA yes, H no. Then again AA yes, AA yes, AA yes. Then it's the very worst case until you reach the end of the end of the text. Yes. So that's why we consider it M by N. Now, the second algorithm is the KMB, and it was developed in 1977 by these three scientists. And it is actually proposed, this algorithm, and it's very easy. The only thing that requires your attention is how to build the table. So first we generate the array and then make use of the array to move the match of the string. So what we need here is actually to find and understand the pattern. We focus on the pattern. So we analyze first the pattern before we start what do you call it, the matching. So first, before I go through this part, I want you to look at this slide and read it and look at the figure before I start. I'll give you 1 minute to try read the text and match it with the figure, and then I will ask you some questions. Okay, so what did you get from this slide? Okay. Type. Let me move to the next slide. I want you to see this table here. Please read it before I continue. Yes, Hannah. We will not start from the beginning, but from where? How to know from where we should start? If we are not going to start from the beginning, from where we should start? And based on what? Okay. Type. See, we said KMB is divided into two stages. Stage 1 is building the table. Stage 2, control the shifting through the table. So it's two processes. Now, to remove the confusion, I would like to rebuild this table by another way. Let me just draw one minute. No, wait. Okay, let me draw it somewhere. Or I much prefer actually to wait. Let's consider this. Let's say I have A, B, A, B, A. This is the same table. Now, this table, this is the pattern, okay? This is the pattern which we are looking for in the text. Let me divide it for you in this way. I would like to add one extra row here. So here is the P, the pattern. Here is the F of J. And here is the pattern of J. And here is the index I. And here is the J. So the index actually starts from 1, 2, 3, 4, 5, and 6. And the J, as you can see here, start from 0. So 0, 1, 2, 3, 4, and 5. Now how to build the function? See the A. Is the A repeated before this position? No. This doesn't appear anywhere. So Fj is 0. B. Is the B repeated before? Can you find it in the anywhere? No. So 0. A. Does it existed somewhere before? Yes. In which index? Index number 1. So that's why I have 1. The second A. Is it existed? Yes. In the same position, number 1. B. In which position? 2. Excellent. And A. In which position? Here is the trick. Here is the trick. Actually, here when we talk about the A, here the B and A, see the B and A, we are talking about BA as block. So the BA as a block appear in position 2. That's why we put 2 here, not 1. Because B here was 1, right? But why I put here 2? Because it's appear as a block BA. So BA as a block is 2, as block 2. So that's why I put 2. But for the second A, it appear in position 3 here, because it is actually following the second block, which is B. So that's why I put 3. So it is 3. So you don't compare only one character at one time. If the character is existed as a block, you have to compare it as a block. So let me show you again. Here, when I started first, I start A as one single character because it is the first character. So it's not appear anywhere. So 0. B does not appear anywhere. 0. A is just a single character, right? So it appear in the first position, which is at position 1. Because here I'm talking about the indices, right? So what I want you to focus in on the indices, not J. That's why I put for you one more row. So here the A, see, A appear in position number 1 here. This is the I. B, sorry, the second A appear in the same position, number 1. Okay, that's in 1. This B appear in position number 2. Here is the B. But when it come to A, this A, it come where? It come after the B, which is at position A. Because this is as a block BA. You got it? Or I give you one more example. I will give you another example so you can understand it much better. See again. Let's say, wait, let me open. Can you see the white screen now? Okay. See this pattern, for example. A. Okay, let me make it in the middle of screen so I don't waste the space. A, B, C, let's say D, A, B, E, A, B, F. Let's build the pattern now, the table. So the table, we have, this is the BI, and we have two more, yes, so this is for I, and this is for B, and this is for the C. Now this is P, this is function F, this is the index I, and this is J. So the index from 1, 2, 3, 4, 5 till 10, and the index, the J start from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now start with the first letter A, 0, B. Okay, before we start the finding the location, I want you to look at the pattern. Can we see patterns here, repeated patterns? We have the AB here repeated, right? And the AB also repeated here, and here. So the AB is repeated 3 times. Yes. So A repeated or not existed before, so 0. B is not existed anywhere, so 0. C 0. D 0. Right? A. Where do we find the A? In which indices? 1. Excellent. B. أيوة. Excellent. Why B2? Because actually here is the pattern AB ends at 2, right? So B at 2. Okay, E 0, then 1, then 2, excellent, then 0. Yes, yes, yeah, Amal. It's not repeated. Do you see the E anywhere? So that's why 0. يعني انت you ask about the E مثلا why it's 0. You did not ask about the D and the C. Same thing. And the F as well. Okay. So this is actually the process of building the table. Do you have any question on this process? Okay, very good. Now let's start using that table in searching. Let me just clear it. Okay, let's say for example I have this letter, or sorry, this T, text D is like for example A, B, A, B, C, A, B, C, A, B. Assume that we have this text. Now I have the button. This is the button A, B, A, B, D. Now it's very simple. Just build first the indices 1, 2, 3, 4, 5, and the J. Now what we care about is the J, by the way. 0, 1, 2, 3, 4, and we have the output here 0. Yes, AB, AB, yes, correct. 0, 0. Then what? 1, then 2. Yes, 1, 2, then 0. ممتاز. Now what we do is to compare. Here we have I starting from the first location, and here we have J. So we compare J, the location J, with I. Does it match? If yes, AA, then what we should do, let me change the color to make it clear for you. In this case, J will be here, will be moved to the second location, and I will move here. Now we compare B with B. Does it match? Is there a match? Yes. Shift J. J, J. Next. B with B. Yes. Shift J with J. Now the next is D with C. So what should we do now? We look at where we stopped the J. The J stopped at, because there is no match. D does not match C. So the B stopped at this position. So the J stopped at this position. We look at this Fi, the function. So Fi said go to position 2. So the J will move to the position 2. So again, the J will move back to this location. But what about the I? Sorry, here is I, not J. What about the I? The I is only one way. It moves forward, this way. There is no backward. So only the J which go backward. The J, I will continue. So we stop here at this point. I stop at this location. So only J will back to location number 2 based on this function. So we start from J equal B. No need to compare the A again. And then start comparing J with this. B, yes, correct. Then shift. C with A, no. A, then what is the location of A? 1. So we have to go back to J to 0. So J will go back 0. So only J is moving backward and forward. Yes. We need to control J again. Wait. No, let me take it out, is much better. Now, first thing is we are using now different counters. Counter I for the text and counter J for the pattern. Now, counter J is actually has the option to go backward and forward. But what controls this movement? What controls this movement is actually what? The function Fi. I think I take out the function Fi. 0, 0, 1, 2, 0. This is the function Fi. Fj, sorry. And here is the Pj. Now, I will start from I equal 1 for the text, and starting from J equals 0, then I will compare I with J plus 1. So j plus 1 means this one. So if just j is 0, I will consider this as 1. But in this case, because we associate j0 to the first position, you can consider it the same location. So we can say that compare the first position in the text, I, with j0. So I0 compared with j0. Now we have, in this case, a match. So A. What I do here is to shift j one position to the right and I one position to the right. So here is I and here is j. Is there a match between the text of I with the pattern of I? Yes. So move to the right. J. Now we compare A with A. Yes. Move to the right. I keep making mistake with the letter J. So move I to the right and move J to the right. Now I compare J with B. Well, J with I. Now we have here B and we have here B. Does it match? Yes, right? So move I to the right. Here we have I and here we have J. Is there any match between D and C? No. So what is the last position for J? Forget about this. What is the last position of J where the text is found? Here, right? When it was at this location, when J is 3. Okay, great. Until here is clear? Yes, exactly. Yes. Now focus on the next step. Now here is J. What is Fj? Because this is the last match at this position. Fj is what? 2. What does this mean? Mean set J to 2. So where is J2? No. J2 means the index at index 2. Not J2 يعني equal J2 at index 2. At index 2 يعني here we are talking about this position. Yes. So what we do is J is here now. See? Let me change the color again. Here is the new J again. طيب, do I need to shift back the I? No. I is one way. So now the next. Where is I? I at this position. I compare from here. From J. B. Do I compare B with C? Does it match? Is there a match? No match. So what is the Fj? Fj is what? F of 1? 0. So I will sit back to 0. So I will start comparing again from position 0. You got it? I then continue matching in this way. Again, I will compare C. Now C is here. I didn't move it. So again, A. Is A match with C? No. Skip. So I will move here. This is the new I. And what? J will not move. J still stick. If next is A, yes, match. Until you reach to the end of the text. Yes, you keep the same process. You got it, guys, now? Okay, excellent. That is actually the core, yani the core algorithm for today. Uh, Let me switch to the sharing environment. Okay, and here is the KMB function written in pseudocode. This is of course the pseudocode, and here the actually what is interesting is the time. Uh, Here the optimal time for KMB is OM plus N. See, it is OM plus N, not like the simple brute force attack. Brute force algorithm for searching where it take M by N. Why we said M plus N? M plus N because M is the time taken. Yes, M is the time taken for building the table, and N is for the searching. So why we said M plus N? Because we build the table only one time. It's not a repeated process. So it is M time for the building the table plus N for the search. It is the opposite way of the what they call it for the brute force. Here is another example. No, what I mean, this is not the optimal. I mean, that is the worst case. The worst case is m by m plus n. But what I said is optimal means is very good. We didn't say this is the best case. Now we move to the binary search, where actually binary search is very helpful. It's based on searching through the nodes, and we have some assumptions. It's actually here uh, where we have the always we have two sides of the parents, the child, and for the child the right side is bigger than the left side, and we don't have any values at the nodes. We don't have any values at the nodes. So look at here, for example, this is a binary search tree. For every node, for every single node has a key. So in the right side of the key we have bigger values, and on the left side we have smaller values. This is how the structure of the binary search tree. And remember, the leaves has no values or no keys. They have no keys, and we call them external nodes. So these are actually the external nodes, and the other one is the rest are the internal node. The internal node. So here for searching for the key, for example, we need to go from the root downward. Let's say you are searching for the value 4, or the key 4. Here, since 4, you check 4. 4 is less than 6, you should go to this path. Then 4 is bigger than 2, then you have to go to the right path. So you will find 4 here. So this is what we mean by searching through the binary search tree. And here in example for the insertion, if let's say you want to insert a new item to the tree, and you have to specify what item. Now let's say I want to insert number 5 as this function 5. So 5 should be inserted on this path because it's less than 6. 5 is bigger than 2, so we should go to this path. 5 is bigger than 4, then it should be an internal or internal node for 4 because it's bigger than 4. So the new 5 will be created here or inserted here. And see, it has also 2 external nodes as child. And this is the pseudocode for the insertion algorithm. Of course, as you can see, we have a recursive function, and we check only the key, and based on whether it's bigger or less, we specify to go to the left side or to the right side. Regarding the deletion, here in this tree, if you let's say you want to delete the item or the key number 4, but see, the case here is a bit complicated because 4 is an internal node. We still have another internal node, a subtree below it, and it is connected with another subtree above it. So let's say you want to remove 4. So in this case, you have to replace it with 5. So let's say you are searching for 4. Before you delete, you have to search for 4. So 4 should be in this path and then this path. So once you specify, you must delete the 4 and its child, its leaf, the leaf child, only the leaf child. That's why we take out the left child. And then we just connect 5 with 2. So W is actually an external node. We call it W. And V is the node itself. Now let's consider removing 3. Yes. If there is no 5, then you delete. Yes. The last level must be leaves with no keys. Now let's remove 3. See, the case here is a bit more complicated. Here we need to copy keys actually, because 3 has 2 internal nodes in both sides. 2 internal nodes. So we need to do some reorganization for the keys. How to do this? First, remove it, but replace it with the key that follows it directly, immediately. Okay, we have to find the internal node, which is what? In order traversal, of course, and take the node that follows it directly. So among the nodes in this direction here, because we have to go to the right? So 3, we have to go to the right because we cannot choose from the left. It will be smaller than the root, which is not possible. Correct? So what is the node or the key which has the value that follow 3 directly? We don't have 4. Yes, number close to 3, which is 5. Exactly. So what we do is to replace the 5 with the 3. 5 with the 3. But we take only, or we delete the 5 and its left child. We keep one child because this one will be connected with the 6. As you can see here. This is the remaining child which is going to be connected with the 6. So the key here, the key point is to copy the key of the closest key to the node, internal node, which we are looking for deletion or deleting it. If they had value, what do you mean? Which one has value? Ah, you mean here? You mean here the 5 here, the one that we deleted, has another value here? Okay, if it has value, does it closer to 3 more than 5? If yes, then go to that level, right? It should be, yani, if that is the case, then it should be closer to 3 than 5. Okay, great. Now, in terms of the space, the search space, of course, we have to go through n elements. That's why it's take O of n for the space. For the space, it take O of n. Now, for the search, it take, of course, O of n or of h. It depends on the search and update methods. So that actually depends on the height of the tree. How many nodes do we have? So the height h will take on, and in the worst case it take in the worst case sorry in the best case the worst case will take O of n, and in the best case will take O log of n in the best case. This is in term of searching. So do you have any question? I hope that it was clear for all of you. We covered the brute force search. I think that is also one part of your TMA, and we covered the KMB algorithm for searching, which is more optimal, and also the binary search tree. And by this we are covering the subject of searching. Yes, thank you so much.